Hello everyone, this is Aarti from CUDA Product Management. I have with me Mike Murphy from the compiler team. We are here to present JIT LTO. In this talk, we will go over the technical details and also show you a demo on how to use this feature. Let's get started. Before heading to the topic of JIT LTO, let's see the rationale for LTO in the first place, link time optimization. As many of you know, without LTO, CUDA programmers had a hard choice to make between kernel runtime performance and device code modularity. For best kernel runtime performance, all the device functions had to be compiled from the same source file because the compiler optimizations are confined to a source file. But this is not always tenable. Device functions can span across multiple files, and therefore we have separate compilation mode to accommodate that. But this came at a cost. Because the compiler cannot perform optimizations that transcend source file boundaries, we saw performance drops up to 50%. And that's when came LTO, link time optimization. By deferring link optimization from compile time to link time, the performance of separate compilation came close to whole program compilation. The linker now has visibility to all the device functions in your application, so it's better able to do those performance optimizations which the compiler could not. Now for this, NVCC had to generate a new intermediate representation. The object file that NVCC produced after compilation were not ptex or sass, but they were LTO-IR. These LTO-IR objects were then linked and optimized to produce sass. JIT LTO takes the same concept for runtime linking. JIT LTO. This was introduced as a driver feature in CUDA 11.4. The most logical place for runtime link time optimization was the CUDA driver because this already supported the ptex JIT linking workflow. All we had to do was simply extend the CULink APIs to accept LTO-IR for link time optimization. The CUDA driver and an NVVM optimizer was now packaged as part of the driver, performed LTO. This came up with some limitations because of the dependence on the driver for link time optimization. Consider this. The CUDA 11.7 LTO-IR, which is version for that toolkit, could not be processed or linked at runtime on an older driver within the same major release like a 11.4 or 11.5 driver. This went against the CUDA minor version compatibility promise, which is any CUDA 11.x application can run on any CUDA 11.x driver. This is not the case with the JIT LTO version that the CUDA driver exposed. And that's why we are deprecating support for this version of JIT LTO. We are not completely pulling the plug on this yet, because we understand your application may be already in the field with LTO-IR in it. So in order to maintain backward compatibility, the 12.x driver will continue to support only the 11.x version of LTO-IR, because we would definitely want a CUDA 12.0 or later application to follow the new way of JIT LTO. Although this is a bit of an inconvenience, it would be worth the porting effort. Let's see what is the new way of JIT LTO. Introduced in CUDA 12.0, we have now a new library called nvJitLink Library. This library is part of the CUDA toolkit. And because it's part of the CUDA toolkit, you'll have to either link it statically or dynamically as part of your application in order to use the APIs that the nvJitLink library exposes. Let's consider this case where you're using NVCC for your offline compilation. So you will be compiling your .cu files into a fat bin with LTO-IR and shipping that. But your main application has to load these fat bins and call into the nvJitLink APIs to do that, and then the nvJitLink API can perform link time optimization on these LTO-IR objects to produce fully optimized sass. This eliminates any driver dependency for your link time optimization workflow. And therefore, the challenges that we had with the prior version with minor version compatibility do not exist. But then again, there are some nuances to the versions of this library that you'll have to take account of. Mike Murphy will go into the details of those in his demo. Let's see what the workflow is if you are using NVRTC. If you're using NVRTC to generate for your runtime compilation, you'll now have to request NVRTC to generate LTO-IR blob, which it will, and then you can use the nvJITLink APIs to JITLink and LTO these LTO-IR objects into producing a fully optimized SAS kernel. Thereby, your offline compilation and runtime compilation needs are taken care of with this new library. Aside from improving kernel runtime performance, there are some other benefits of JIT LTO depending upon your application. Let's consider the case where JIT LTO can actually lead to a considerable reduction in binary size. Take this simple math library which performs some kind of a matrix operation depending upon the user input of the matrix dimension itself. Because your library could be used in a wide variety of application contexts, the library developer is perhaps shipping a specialized kernel for each dimension of matrix multiplication or operation that they care about. And in addition to doing that, because the target system could have different GPUs, they probably want to ship this entire kernel in multiple different SAS for different SM architecture. And they are doing this perhaps for every module in their library. You can see how a library can quickly grow in size, especially considering the number of GPUs that they have to support. Come JIT LTO, let's see how it could be different. Instead of shipping the entire kernel, now with JIT LTO, you're actually shipping building blocks, smaller building blocks with in LTO-IR format. And because the kernel itself is JITted at runtime, there is a possibility that you can take the user input of matrix dimension at runtime as well, and therefore you're composing the right kernel for your target configuration, even taking into consideration the GPU of the target system, and then JITting to a SAS. So instead of shipping fully formed kernel for every module, for every SM architecture, for every specialized kernel configuration, you just have to ship the building blocks and using LTO-IR. Isn't that a cool trick? Let's consider another case where JIT LTO can be used in the context of user callback routines. User callback routines are kernels that are supplied by the user but invoked in the context of the libraries themselves. This could be for some kind of a pre-processing and post-processing, for example, for loading or storing data back. In the case of without JIT LTO, the user callback routines are SAS kernels, and the libraries have to make indirect calls to invoke them. And that can be additional cost and expensive, depending on how many user callback routines the libraries end up calling. In the case of JIT LTO, now the user callbacks can also be shipped as LTO-IR in addition to your library. So the user callbacks can actually be inlined into your library code, forming a monolithic kernel which can be better optimized. And those are some interesting uses of JIT LTO. Please let us know if you find some other interesting uses for it. And now we are heading to the most interesting part of this presentation, demo by Mike Murphy. Mike, please take it over.
Hello, everyone. Thank you, Arthi. And I now want to give a demonstration of how to use the new nvJITLink library. And so I'm going to share my screen here. And first, I want to show how you can use the nvJITLink documentation. If you go into our regular toolkit documentation area, there is now an nvJITLink user guide, and that has a lot of good information for you. So I suggest looking there. Also, in the samples, oh, I'm in the wrong place, sorry. I was looking somewhere else here. Actually, you go to samples now, section 4, CUDA libraries, and you will see that there is a JIT LTO sample for you. So I suggest looking there at that sample. In fact, I'm going to be using a variant of that sample for this demonstration. So speaking of which, let's actually look at that code. So the first thing to note when you want to use nvJITLink, of course, is there's a header file, nvJITLink.h, which you'll want to include. And then going to the actual code, it's pretty straightforward. In fact, if you've used the CULink APIs, it is basically the same APIs, just different names. So it starts off with an nvJITLink create, and then you add your inputs with add data or add file, and then you're going to actually do the link and that return. That's basically it. One difference you should know about compared to the CULink APIs, if you were to use them, is that, so well, first of all, when you look at this, you create the handle, and so we're always passing in this handle everywhere. And then in the CULink create, we also pass in options. And in this case, there's two options. There's LTO, and I will want to point out here that you don't actually have to use LTO to use nvJITLink. You can just do a JITLink of like Kubins and not do LTO. LTO is like the more advanced case, and so that's the case we're going to demonstrate, but it's not required to use LTO. So in this case, we're using LTO, and then we're also specifying the architecture. And this is one difference from CULink. Because CULink was part of the driver, it was able to implicitly look at what chips you have on your system and target those without you actually having to say anything. In this case, now because nvJITLink is a toolkit library, it's separate from the driver basically, and so it doesn't know what architecture is on your machine. So you can either hard code the value like SM90, or you could use driver calls, which is what this does, CU device get attribute, major and minor, and using that you can actually compute the architecture that you want to generate for. So somehow you specify the architecture, and then you want to add your inputs. And we're showing the two different ways you can add it here. As Arthi mentioned, you can generate your LTO code on the fly with NVRTC, or you can compile it offline and then pass that in. So in this second one, nvJITLink add file, we are using an offline compiled compute.o. In both these cases, we have to specify what the input is. In this case, it's a host object. In the other case, it's LTO-IR, which has been generated by NVRTC. And then after those, you then actually do really the bulk of the work is in nvJITLink complete. This is where the actual merging, optimization, relocations all happen. And then after that, in this case, we're going to check for errors, which is always a good thing to do. You can get an error log and print that out. But after that, you want to get the linked Cuban, your result from doing the JIT link. And now you don't know ahead of time how big that linked Cuban is going to be. So what we do is we give you a way to figure out the size of that, and which you can then malloc into some space that you want to control. And then we'll store the linked Cuban into that space. And then after that, you would just pass that linked Cuban to CU module load data, which is a driver routine that loads in a Cuban. And it's also, of course, good to destroy the handle and the memory that's associated with it. That is basically it. It's very similar to the CULink APIs if you're used to them. Same kind of thing. You create a handle, you add your inputs, you do the link, and then you destroy your handle. So given that, and then to actually invoke it, you do something like you basically pass nvJitLink on your link line. So in this case, we're doing G++ of the C++ file. We set up our include and library paths, and because we use nvrtc as well as nvJitLink, we link both of those in, and then we just run it. And when you run it, you will see that it prints, this does a SAXB computation, so it prints all this data and then says passed at the end. So that's great and easy. What kind of problems might you run into, and why do we even switch from CULink to nvJitLink? So a lot of that has to do with the versioning aspect. So now, if everything on your system is the same version, your driver, toolkit, your LTO inputs are all from 12.0, then everything's fine. You're not going to have any problems. But what if you have a mix of things? For instance, on this system, I have a mix of 12.0 and 12.1, which is our upcoming release of the toolkit, as well as I have stuff from the release that's going to come after that. So I have a mix of versions on this system. And when you do that, you do have to be a little more careful about versions, particularly about future versions. So for instance, if I was to take a 12.1 generated LTO-IR and try and load that with a 12.0 nvJitLink, it would not work. In fact, I have a script to do that. And by the way, I'm using scripts here because I don't want to take the time to install, uninstall toolkits and all that kind of stuff. So I'm doing some magic with paths and environment variables. Please just trust me on this. I'm not trying to like trick people. I'm just trying to save time, okay? So the case where we have a newer LTO input, but an older nvJitLink library is, oops, sorry, I did not type that correctly. It's this here. And you will see when that happens, it tells you the NVMIR version. And by the way, NVMIR is the same as LTO-IR. We should probably update this to use the same terminology, but it's really the same thing. Because that version is newer than the tool, in this case being the library, nvJitLink, and it tells you that the nvJitLink add file of compute.o failed, and that you may need a newer version of the nvJitLink library. So if you instead were to use the 12.1 nvJitLink library with this, that is this script here, and then it all works. So the other thing to know about the input files that you give to this is that, so we call these LTO-IR. Our LTO-IR is based on LLVM, which is an open source framework that the compiler uses. And open source is wonderful in a lot of ways, but one disadvantage of it is that we don't have complete control over it. And in particular, LLVM does not guarantee compatibility across releases. So what NVIDIA has done is we are saying that we will guarantee we'll do whatever it takes to make things compatible within a major release, like 12.0, 12.1, 2, etc. But we will not guarantee compatibility across major releases, so say like 13.0. So you can use like 12.0 generated LTO-IR for any of the 12.x nvJITLink libraries and drivers, but across from that, you may need to recompile. And that's one of the reasons, one of the issues that we actually had with the CULink idea where it was in the driver, because it's in the driver, it was not keeping up to date with the toolkit. Driver and toolkit, if you install them in the same thing, everything's fine, but they can get out of sync where you can have a newer toolkit or an older toolkit relative to the driver. So by keeping the compiler optimizations as part of this toolkit library, we're able to keep things compatible to be used as long as you're using within the same major version. So the other thing to look at is the library itself. Now, nvJITLink Library is actually released in two forms. There's the shared library and a static version of the library, which is nvJITLink_static.a. Why do we have a static? One reason is because maybe you want to release this into an environment where there is no toolkit. So if it's a shared library, then there has to be a toolkit there to find the shared library in order to run it. If you've built the static library, then the static library gets basically embedded into your application and can be moved around wherever you want. Now, this ability of shared libraries, where it can be different where you run it from where you build it, means you also need to be careful that those are compatible. So if you build with, say, 12.0 and run with a 12.1 nvJITLink library, you're good. Everything's fine. But if you were to do the reverse of, say, build with 12.1 and try and run with 12.0, well, that's not going to work. That's going to give you an error like what I will demonstrate right here. You're going to get this lookup error, undefined symbol, nvJITLink, get linked Cuban 12_1. This is because I'm trying to run it on nvJITLink 12.0, and so it doesn't know about the 12.1 versions of the library. That's another thing that you have to be aware of. Now, what about the output of nvJITLink library and running that on the driver? So the good news is we have CUDA minor version compatibility. If you're not familiar with that, what that means is that a 12.x driver will run any 12.x generated Cuban. So, for instance, on this system that I'm demonstrating, I have installed a 12.0 driver, and I can generate with my 12.1 nvJITLink library a 12.1 linked Cuban, and I can run it on the 12.0 library, and it works fine. So that is all good. And so that's basically some of the versioning things that I just wanted to demonstrate so you can be aware of them as potential pitfalls. But in general, the idea is you want things to be in the same version or greater, and then you're always fine in that case. And I think with that, I'm going to pass this back to Arthi to wrap us up. Thank you.
Now is the time for a wrap up. JIT LTO has some interesting benefits. You can retain source code modularity without compromising kernel runtime performance because you're shipping the building blocks for an entire kernel using LTO-IR. You're now having better composability of kernel at runtime, also much smaller library sizes. But there are no free lunches. There are some gotchas that we'll have to invariably deal with. Because the entire compiler optimization is deferred to link time and now linking is happening at runtime, there is an overhead that might be in the critical path for your application. You'll also have to make sure you have the right version of nvJITLink, either by statically linking it or you have dynamically linking. You have to make sure that the right version of nvJITLink is present in your target system. You'll also have to ship PTEX if you want to JIT to a future architecture. There is a technical blog for those of us who prefer to read and refer to blog. That blog goes into the details of some of what we discussed today and also shows a specific use case of an NVIDIA library that uses JIT LTO, and we are sharing some interesting performance numbers that you could review. That said, thank you all for your time listening to our talk today. We do have CUDA 12.0 update 1 available for download, and there is also a webinar we did recently on the CUDA new features and beyond that talks over all the features that we introduced in CUDA 12.0. Please do take a look at it. As always, please leave your questions, comments here, or we do have a very active and vibrant developer community on NVIDIA's developer zone. If you're a registered user, please do ask your questions regarding JIT LTO. We will be happy to get back to you. Thank you.